When you start on a quest, you don't know exactly where it's going to take you, but you might have some sense of what you hope to find. And although everyone embarking on this quest has their own individual aspirations, I think we also have a shared vision of what a truly intelligent platform would look like. It's the kind of intelligence that would be able to learn concepts or causal relationships from just a handful of examples. An intelligence that could learn to move by itself and transition seamlessly between small movements, holding a pencil or a glass, and large ones, riding a bicycle, or navigating upstairs, or under tables, or through puddles. An intelligence that could acquire natural language and use it productively, and maybe even explain to us what it's thinking. An intelligence with sophisticated social cognition, one that could hear the tone of your voice and guess what you're feeling, and that could be helpful both in concrete ways, opening the door for you, and in more abstract ways, guessing what kind of problem you're working on and proposing partial solutions or partial plans. Maybe even an intelligence with rich symbolic representational abilities that could stack blocks vertically and say it's a tree, or stack them horizontally and say it's a train. One that could see past what things actually are to what they might mean or what they might become. This kind of intelligence might seem almost unimaginably far away. But if we are going to succeed at engineering it, we first have to understand it. And the good news is that we already have a platform right here at MIT that can do all of these things. Before I tell you more about it, though, I should tell you that the existing platform has a few limitations. For one thing, although it engages in unsupervised learning in a machine learning sense, most of what it learns from raw, unlabeled data. It requires actual supervision almost every hour of the day. It estimates risk very poorly, and left to its own devices would quickly self-destruct. Additionally, for very poorly understood reasons, it needs to be connected almost continuously to other platforms, much like itself. Absent that connection, it falls apart very quickly. But the main thing is that although we understand many fascinating things about its capabilities, there's far more that we do not know. And I believe that understanding how this system works is going to be the key to our understanding how intelligence works. The unbelievably sophisticated platform I'm talking about is, of course, the one housed inside the minds of our infants, toddlers, and preschoolers. They can't drive cars, but they can manipulate objects and move their bodies through space with a flexibility and coordination roboticists can only dream about. They can't recognize a million faces with high fidelity, but they can look into a single face, even one with a non-canonical emotional expression, and tell quite a lot about what it is thinking and feeling. They can't look 20 moves ahead in a game of Go, but they can imagine possible worlds literally as child's play. And although there are many things still to learn, we are beginning to understand a lot about how this kind of intelligence starts and how it grows. We have known, for instance, for decades that Piaget was wrong. There is no stage at which infants are only sensory motor learners. There is no stage at which children are only concrete learners. Infants are abstract learners from the start. They have abstract representations of objects and forces and number and agents and goals. And as you'll hear soon from Rebecca, we're beginning to understand how we can look at the neural bases of some of these abilities and see structure and functional specialization in infants' brains. But we also know that the ways children learn go far beyond pattern detection and prediction right from the start. Just restricting it to work from students in my own lab, we know that 15-month-old babies can tell when evidence is sampled randomly or selectively, and like us in science, they draw broader generalizations from randomly sampled data. We know that 15-month-olds can use just 2 trials of covariation evidence to decide whether an action failed because someone did something wrong or because something is wrong out there in the world, and they choose to seek help or explore accordingly. We know that 15-month-olds can look at an adult trying to achieve different goals and estimate how hard the adult was trying and use this to calibrate their own persistence on their own tasks. We know that by preschool, children explore when evidence violates their theories, and they both select and design interventions to isolate variables. We know they posit and search for unobserved variables to explain away anomalous data. And we know they can even reason about what kind of evidence other people might use and when it is likely to change their minds. We also know, of course, they have very sophisticated social cognition. We're beginning to understand a little bit about that. They reason for something we might think of as a naive utility calculus. They can use the fact that someone finds a task more or less difficult to reason about what the person prefers. They can use knowledge of the person's reward structure to reason about what they might find more or less difficult. And at 2, they can use this naive utility calculus to make moral judgments. If you refuse to help them, they think that's okay if the action was costly, but not if the action was easy for you. Finally, we know that even 15-month-olds recognize emotion, and not just the difference between positive and negative emotions, or 5 basic emotions. They can tell empathy from excitement, from amusement, from anticipation, from a 2-second vocalization, and they can use others' emotional reactions to both identify and search for their probable causes. As Josh Tenenbaum will go on to tell you, if we could get machines to do even a fraction of this, we'd have made huge strides in AI. However, it might seem a little hard to believe, because if we walked out of this room and peeked at the remarkable behavior where this is all taking place in our daycare centers or across the river at our labs at the Boston Children's Museum, you would see that the most powerful learning platforms in the known universe are right now, even as we speak, playing with sand, talking to stuffed animals, and clambering up slides. But although I cannot tell you whether we will have human-like AI in 10 or 20 years, I guarantee that those children playing in the sand right now will be using all the technologies we have invented in 10 years, and in 20 years, they will be inventing technologies and maybe even societies we are not right now able to imagine. I think understanding this kind of learning is the key to our quest for intelligence, and fortunately, we are right now on the cusp of a new technology that could give us much greater insight into the minds of babies and children than we have ever had before. For the past decades, we've only been able to test the children we can bring into the lab individually. So it's been incredibly laborious to get any data, let alone data sufficient to test the predictions of quantitative models, or look at individual differences, or test the effect of different interventions. But we are right now here at MIT nearing the completion of an open source, online developmental lab where we can conduct behavioral studies of children over the internet in parents' homes. It's not video conferencing. You can Google it, put your child in your lap, and run the experiments yourself whenever you want. This platform, Look It, is currently in development, but if we can bring it to scale, we could have hundreds, even thousands of children in studies rather than dozens. This online lab could go a long way to making developmental research more robust and more reproducible, and it could give us the kind of data we need not only to test the predictions of the models of intelligence that we're going to engineer, but to inform and constrain the kinds of engineering we want to design. We already know the demographics of the population we get on Look At look more like US Census data than almost any developmental studies in the literature. And we know that we can collect almost all the kinds of data we can get in the lab in this way. Advances in this kind of technology will teach us about the ways children learn in a way that will tell us a lot about what kind of learning is possible for us, but also for the machines we might try to build. I'll end by noting the archetypal quests from the Odyssey to the Wizard of Oz often involve people traveling vast distances over terrain, only to discover what they were looking for was actually much closer at hand, right at home with them all along. I think the MIT Intelligence Quest will take us to remarkable places and enable us to build remarkable things. But I hope it's also the kind of quest that will bring us back to ourselves and a deeper understanding of who we are and of who our children might become. Thank you.
You are just the best.